workshops to choose from. Our graduate is the leaders of many companies and ministries in Saudi Arabia. For example, the ministry of the company Aramco, which is the neighbor company to us, it's the largest oil company in the world. They have 28 VP and senior VP. And out of this 28, which are the leaders of this company, 24 is a KFUBM graduate. And if you go to SABIC, to many big universities in Saudi, big companies in Saudi Arabia and many ministries, you will find a big percentage of these people in the leadership from KFUBM. So it's just to let you know how good is KFUBM and how we are proud of our graduates. And of course, our faculty is an excellent faculty, and we have examples here from the faculty who are organizing this workshop, Women in Data Science workshop. They have an impacted research that generated lots of citation and patents and excellent outcome of these research. So finally, we would like to thank all of the time and effort to attend this important workshop. I would like also to express my great and appreciation to the distinguished speakers, Dr. Husseini from Tufts University, Dr. Tomasel from SSTAN, Argentina, Dr. Zahang from KAUST, and Dr. Sinan from Aramco. Thank you very much. I wish that you are there in March. Unfortunately, we have to postpone this meeting because of COVID-19. It was a missed opportunity to have you there, but there is a big chance to have you, inshallah, in the next workshop. And we will invite you again to this workshop and to see the universities and the surrounding area. I would like also to express my thanks to all the members of the workshop who work hard to, inshallah, make this inshallah, it will be a successful workshop. Special thanks to Dr. Rab Aziadi, Dr. Manal Al-Ataibi, Dr. Iman Bidlawi, Ms. Iman Al-Majdoui, Abdulaziz Al-Naim, Fatima Al-Mash'an, and Hassan Al-Mutlaq. Thanks to all of you. And we wish everyone a knowledge and based, productive workshop. Thank you very much.
Okay. Assalamu alaikum wa rahmatullah. Hello, everyone, and welcome to the first Women in Data Science Dhahran workshop event that we're holding today virtually from the KFUPM campus here in Dhahran, Saudi Arabia. I'm Dr. Rabia Zaidi, the Assistant Professor of Computer Science and the Ambassador of Women in Data Science Dhahran. And I'd like to extend to you all a warm welcome to today's workshop that is held in cooperation with the Female Education Division at KFUPM as part of the annual Women in Data Science Worldwide Conference organized by Stanford University. The Women in Data Science, the Women in Data Science is a worldwide initiative that was launched initially as a one-day conference at Stanford University almost 5 years ago in 2015, with three main goals in mind. The first is to globally inspire innovation in data science by highlighting role models who have distinguished themselves in the field and showcasing various opportunities in the field of AI. Sorry about that. And showcasing various opportunities in the fields of AI and data science. The second goal is to educate all participants, regardless of gender, about cutting-edge research and technologies and future trends in data science. The third goal is to support women who have chosen to pursue a career in the field of data science by providing their work with exposure opportunities, allowing them to expand their networking connections, and energizing them to continue to pursue more opportunities in data science and AI. At the time, the conference was watched by over 6,000 people, and it has since become a global movement that features a wide range of educational activities, including a conference, a datathon, and a podcast series and educational outreach programs. The workshop we hold today is one of over 150 worldwide Women in Data Science regional events that are held in conjunction with the main conference at Stanford. It is our great honor here at KPPM to hold this prestigious workshop as our inaugural national event since the founding of the female division in August 2019. It is especially relevant to our region as the Women in Data Science goals perfectly align with the objectives of the Saudi Vision 2030, which has at its heart the goals of implementing a comprehensive AI transformation in the kingdom, as well as enabling and supporting Saudi women. The timing of the workshop couldn't have been better, as it is being held exactly 1 week after Saudi Arabia hosted the Global AI Summit under the patronage of His Royal Highness Crown Prince Mohammed bin Salman bin Abdulaziz Al Saud, where a national strategy for AI has been announced, revealing the kingdom's plan to become one of the top 15 AI pioneers by 2030. By focusing on stimulating the AI market through research and innovation, which we aspire to promote and enrich through this workshop today. Although the pandemic has imposed an isolation on society, we are hoping that by holding this workshop virtually, we will alleviate the effects of the pandemic on outreach and scientific engagement. I would like to conclude with welcome you once again. Our exciting program includes talks by distinguished women data scientists on pressing topics in the kingdom, from biotechnology to natural language processing and AI for smart cities and the oil and gas industry. And please stay tuned, as we will also have 2 video streams from Stanford's main conference 2020 from this year. Thank you, and I hope you enjoyed the workshop.
Data science and any data-inspired and data-driven science is so critical right now. More and more decisions are made based on data. The amount of data that we gather every day and the insights that the data can provide us is just growing exponentially, and that is no exaggeration.
The market for data science and related areas like AI is booming.
It is so important to have women in artificial intelligence, in the area of data science, and also in leadership roles. It's being able to use data to solve issues and understand bigger problems. It's critical, and we need women in these roles. Every individual brings their own perspective, and so we need to make sure the entire workforce is represented.
And the good news is there's so many jobs and many different ways to combine their passion area and their skills in data science and get involved.
I would like you to say, what are the problems in the world that absolutely have to be changed? And, can you individually, given all the amazing background that you've had so far and all the education that you've got so far, what are the unique things that you can do to change the world towards that mission? And then think of the technology.
If that is going to become completely data-driven over time, then you can't miss that opportunity. You've got to join in and have your say.
If you're not looking at the data from all sorts of different angles, then you could introduce a lot of bias. So it's really, really important that we have around the table all genders, all races, all backgrounds.
We can't ignore social and structural problems. We can't just go in a corner and write some code and read math and then that's the solution, right? Can't do that. So we have to think about who's being affected by these algorithms.
Welcome to WiDS!
When we first started this conference, we never would have imagined that we'd be sitting here today with over 200 regional events. We've got over 500 WiDS ambassadors worldwide. Many of them are women, but we've also got a lot of men. And these are people who are just passionate about inspiring others within their community. We're in over 60 countries, and year after year, we're blown away.
Let's make this next decade the Women in the Data Science decade.
What I love about it is that growth is viral. That people will attend one event in one city and then they'll want to bring it to their cohort or colleagues the next year.
This type of industry can be done everywhere, so it should be accessible to everybody. And this is one of the reasons why I love that we are global with WiDS.
So we wanted to create opportunities for women to inspire, educate, and support women at many different times throughout the year. And one way that we decided we could do that was through a datathon every year, which is a predictive analytics challenge using real-world data. We have over 900 teams from 85 countries, and that's in every continent except Antarctica.
When we started WiDS in 2015, we had no idea this was going to be a global movement with tons of international events and a datathon and a podcast show and now outreach to middle school and high school. It's just been such a ride.
Our latest endeavor is to work on some materials that we can hand off to teachers in schools around the world.
This has provided a platform for literally hundreds of women, if not thousands of women, to have an opportunity to be heard.
But the truth is, these are really simple experiments, but they had profound impact because they empowered someone else to be able to do their job better or to be able to take that message.
5 years ago, when we were sitting around a coffee table thinking about what WiDS could be, I never in my wildest dreams thought it would grow so far and so wide around the world in just 5 years. What I'm most excited about is the next 5 years, because I think this is really just the start.
Welcome to the first session of the Women in Data Science at Dhahran. I am Dr. Iman Budaliwan, Assistant Professor at the Information and Computer Science Department at KFUPM, and I will be chairing the sessions of this workshop. I am very thrilled to introduce our first speaker for today's workshop, Professor Suha Hassoun. Professor Suha Hassoun is a professor and past chair of the Department of Computer Science at Tufts University. She holds secondary appointments in the Department of Chemical and Biological Engineering and also in the Department of Electrical and Computer Engineering at Tufts. She received her bachelor degree from South Dakota State University, her master degree from MIT, and PhD degree from the Department of Computer Science and Engineering at the University of Washington. Soha's research interest is in the area of biodesign automation, where her lab aims to build tools for analyzing and designing complex biological systems. Soha was the recipient of the NSF Career Award and several awards, including the 2000 and 2007 SIGDA Distinguished Service Award and the 2002 SIGDA Technical Leadership Award. She held executive and technical leadership position at several conferences and workshops. She is a fellow of the Tau Beta Pi and a senior member of IEEE and ACM. She's committed, Soha is an educator, and she's committed to providing opportunities for students to learn, to practice their profession, and to be authentic in themselves, regardless of societal and self-imposed roadblocks. Please join me in welcoming Professor Soha Hassoun for the first talk of this workshop. Professor Soha, are you here with us?
Yes, I am. Yes, I am.
Okay.
Let me just share my screen.
Yes, please. Yes, we can see your screen now. You can
just give me a second. I'm almost there.
All right.
All right. Is this good for everybody?
Yes, crystal clear.
Sorry, there's too many parameters to set up here. Thank you very, very much for this very kind introduction. I really appreciate it. I'm delighted to join you here today in this wonderful, wonderful, wonderful event. I wish I was there in person, but it is what it is. I very much hope everybody is doing well, as best as possibly one could do under the circumstances of the pandemic. Today, I would like to talk about artificial intelligence and its far current and future-reaching impact on our lives. I would like to also highlight some projects in my lab that use machine learning to advance biotechnology. This is one of my favorite quotes. It's from a person by the name of Jensen Huang, who is the co-founder and CEO of NVIDIA. NVIDIA is a company that started in 1993 making processors for gaming and multimedia applications. NVIDIA quickly evolved into a business of making GPUs, or graphical processing units, around the year 2001. In GPUs, the same program can run in parallel on multiple streams of data. This type of hardware is very appropriate for graphic cards that update every pixel on the screen simultaneously to maximize the experience for gamers. What's really exciting and relevant about NVIDIA's hardware and GPUs in general is that GPUs do not just work for graphics. GPUs can be used to perform complex computations required by machine learning and artificial intelligence algorithms. This quote was provided by Huang in 2017 in reference to the state of software. At the time and currently, very few lines of software in the world implement AI algorithms. All what Huang was saying here is that once various disciplines start using more AI algorithms, AI will become the dominant form of software. GPU hardware, like the one from NVIDIA, is enabling a software revolution. Today, I'd like to highlight the impact of this revolution. Machine learning and artificial intelligence have been around for a while. The interest in this topic dates back to the 1950s, where computer scientists wanted to replicate human intelligence in various forms. For example, they wanted to make computers that could solve algebra word problems. or computers that could prove theorems in geometry, or computers that could learn how to speak English. The renewed interest in machine learning and artificial intelligence came from the work of Geoffrey Hinton in 2012. Geoffrey is a distinguished researcher and well known for his work in artificial neural networks, especially how they could be designed to learn without the aid of a human teacher. His idea is that neural networks, like the human brain, may start autonomous intelligent machines that mimic how the brain works. Geoffrey did not come up with this idea overnight. And this is very, very typical with researchers. You don't think about things overnight. It takes years and years to develop ideas. His undergraduate degree was in the 1970 in experimental psychology. His PhD was in artificial intelligence in 1978. So you could see it took him a really long time and studied really, really hard and developed this technology from 1978 till 2012, and he still continues to do that today. So they had this big breakthrough in 2012. They showed that deep neural networks can be trained on images to identify things like mushrooms, a leopard, and a Dalmatian dog. This work was shared widely and very much got the whole world excited about artificial intelligence and machine learning. Let me give you an overview of deep learning and how it's shaping AI. Deep learning is achieved using a computing structure known as a neural network. The neural network is simply a layered network of nodes. So here's my input layer, and I have 2 layers here and an output layer here. Each node or circle here performs a calculation based on a parameterized function. The outputs of these nodes are typically a number between 0 and 1. The input for the network is comes through these yellow nodes on the left. The final outputs are computed in the red nodes here on the right. The inputs to each node is based on the outputs on the nodes from the prior layer. And this type of neural network architecture is referred to as a feed-forward neural network. Let's say we want to use this type of network to classify if an image is that of a cat or a dog. That is, we want to feed the neural network this image, and we want it to tell us out here the likelihood of the image being that of a dog or being that of a cat. So when I feed the neural network a picture of a dog, I want the neural network to say the likelihood of the image being a dog is high, and the likelihood of the image of the cat is being a cat is low. If I feed the neural network a picture of a cat, I want the neural network to say that the likelihood of the cat is high and the likelihood of the dog being low. If the picture here or the image is not of a cat or a dog, then I want the neural network to say that. I want to say the likelihood of being a cat is low and the likelihood of being a dog is low. So how do we make this neural network learn to produce these answers? We have to train these neural networks such that each of the functions associated with these green nodes learn a particular parameters or set of parameters that will allow the neural network to produce the right answer. And let's say we have a lot of data. Let's say I have 1 million images of dogs and 1 million images of cats and 1 million images of other animals. For each image, we feed them in an ordered fashion as the input to the neural network, and we keep adjusting the parameters of all the nodes in the green circles here to make sure that we get the right answer is computed here. The work of people like Geoffrey Hinton opened the doors to exploring such neural network architectures, not just for images, but for many, many other data types. Now that we know a little bit about what's behind the AI revolution, I'd like to share some examples of how AI is transformative. And by transformative here, I mean something that causes an important and lasting change. My first example is about self-driving cars. Engineers have been trying to build prototypes of self-driving cars for decades. The idea is really simple. Place cameras in a car, cameras will track the objects around the car, and have the car drive itself without input from the user to get from one place to another. Clearly, the car has to react to avoid hurting any humans or running into objects. So we could think of this problem as related to both hardware and software. The hardware collects the data in the form of cameras. That's the easy part. The software organizes this data and compiles it. On the software side, the input data is processed through machine learning algorithms that are trained in real-world scenarios. It's machine learning technology that is the center of self-driving cars. My second example is that of facial recognition. A facial recognition system identifies or verifies a person from a digital image or a video frame. There are multiple methods in which facial recognition systems work. But in general, they work by comparing the selected facial features from a given image. Here's some feature examples with those features of images of faces in a database. We could think of this task as biometric artificial intelligence application that can uniquely identify a person by analyzing patterns based on the person's facial texture and shape. This technology is now widely used and allows us to control access to all kinds of devices. My third example is perhaps the most astonishing and powerful application enabled by AI. AI can invent things on our behalf. Just take a minute and think about that. In the prior two examples that I gave you with the self-driving car and the facial recognition, we invented the systems. We knew what we wanted to build. But AI can invent things on our behalf. Let me show you an example on how AI can invent new faces. Consider this neural network here in the upper right corner of my screen. My input is fed from the left, and it gets compressed as represented by the outputs of these red nodes. And then the output of the red nodes is fed to the yellow nodes. And I train this neural network to reproduce the input at the output of the yellow nodes. So if I feed an image to the blue nodes, I will train the neural network to produce the same exact image at the output of the yellow nodes. You might say this is kind of funny, and why should I do that? So all what I'm doing here is I'm encoding the image into a smaller representation at the output of these red nodes, and then decoding it to reconstruct the original image back. I can train the neural network with lots and lots of data to do this well. But I could also train the neural network to learn the distribution of the data at the red nodes. Training the neural networks to learn the distributions turns out to be a very useful aspect of neural networks. Let's say I have lots and lots of images of people's faces. If I train the neural network on the faces, maybe the top row that I learned as it relates to the input image. So if my distribution says pick green eyes 20% of the time and brown eyes 80% of the time, then I will produce an image with green eyes 20% of the time. This allows me to create lots and lots of different images based on one original image. Taking an example here of the images on the left, look carefully. All the images have some commonalities, but you can see various distributions in hair colors, darker hair colors towards lighter hair colors. There's no glasses in some places, and there's glasses in others, and many other such features. I want to emphasize here that the red nodes that I have here do not represent a single feature, like the eye color, like I described, but it's a features or a group of features in some kind of compressed form. I don't really have a clear understanding what this red node represents. But I do have a distribution on whatever this thing represents. And when I'm trying to generate new faces, I'm sampling from the distribution in these red nodes. Again, the idea here is that AI can invent things for us. And with this techniques, which is called autoencoders, we could do a lot of things. For example, if you do any gaming, you could invent lots of different virtual backgrounds for gaming. From my interest, I could invent lots of different molecules based on one kind of molecule that I feed in. And autoencoders are used in many other applications. So you've heard me talk quite a bit about data, and you've heard the word data, big data. Just to give you an idea on the size of various data, let's say you could store 1 byte of data on a grain of rice. A kilobyte is equivalent to a cup of rice. A megabyte is 8 bags of rice. A gigabyte is 3 containers, container lorries, and so on. A zettabyte, that's 10 to the power of 21, is equivalent to filling the Pacific Ocean with rice. Not just the surface, the whole ocean with rice. So the new software revolution in the form of AI, combined with the availability of big data, is creating some exciting opportunities for us. When I look at AI and data science, I think of us as being at the intersection of several areas: math and stats, hacking and coding, and domain expertise. And domain expertise means that you have experience in a particular application. For example, health records, or geographical maps, or e-commerce, or digital marketing, and many others. And to be proficient in AI and data science, you must know one such area very, very well, but you need to speak the language of the other 2 areas. So indeed, if you work in this area, think about being trilingual. So I'd like to shift now and focus on AI for biotechnology, and specifically about the work that's going on in my lab. My lab focuses on using machine learning for biological discovery. My group builds software to allow the analysis and design of biological systems. We would like to learn what these biological systems do, and we also would like to engineer them and build new ones. We also think very carefully of machine learning algorithms and how we can improve them to achieve these goals. I always think about redesigning biology and not just engineering biology, because we never start from scratch. We always, or typically, we modify existing organisms or existing systems or study them, as I will describe shortly. Before I tell you about my lab does, I'd like to start by giving you some examples of some biotechnology areas that really get me super excited. One area of interest is designing custom organisms. You could take bacteria like E. coli or yeast, and you could redesign it to make it do something useful. For example, we can make E. coli a biological factory and make it generate molecules of interest. Some molecules of interest are like perfume or sweeteners or biofuels. Here you have to understand the biology of the bacteria, and then you have to figure out how to add to the bacteria material to make it produce these high-value molecules. There's a company called Ginkgo Bioworks in the Boston area, and this is actually a picture from their wet lab. Their specialty is making these custom organisms. And they've developed an amazingly complex design systems where they could customize organisms in many ways. So I'm interested in figuring out, how do I build tools to help people like Ginkgo Bioworks actually design these custom organisms? Another area of interest to me is the human gastrointestinal tract, or the GI tract. The GI tract has 10 to the 14th different bacteria belonging to several hundred species. These species are referred to as the gut microbiota. These bugs eat what we eat, and the bug community does important work in the human body. They produce molecules that play critical roles in health and disease. They produce important molecules, such as vitamin K and B12. I'm interested in analyzing the molecules produced by the gut microbiota. I'm also interested in learning more about biomarkers in the human body. Biomarkers are just molecules produced by human body and measured in blood or urine. We've already seen some remarkable work in identifying some biomarkers for particular human conditions. In recent work published in Autism Research, scientists at NeuroPoint DX, in collaboration with others, reported new findings from the Children's Autism Metabolome Project. The research identified unique groups of molecules in over 50% of the children with autism in the study. This is an important step towards the goal of developing molecular tests in blood or urine that could form the basis for a biological screen to analyze the risk of autistic spectrum disorders. There are many other studies that rely on identifying molecules produced by the human body and the gut microbiota, including those focused on exercise and weight and health applications. I'd like to take a minute to tell you why working with biology is very difficult. Compare redesigning biology with the building of a smartphone. Okay. When I'm building a smartphone, I know so much about electronics. I know so much about physics. I know what atoms do in a smartphone. So here, what we're doing is we're thinking about designing a next generation smartphone in a future technology, not the technology we have now, but several years out. And we don't have any schematics or specification about how the system works. We don't know that information. We didn't invent that information. But we can only observe the behavior of the system, which is very much context dependent. And your smartphone could have babies and die very quickly and reproduce. And we don't understand fundamentals of the material used in smartphones. So Bernard Pearlson, who's a very famous system biologist, described this about E. coli. E. coli is the most studied organism on the planet because it's a very easy bacteria to manipulate and to do experiments on. He said that we probably just understand 1 out of 4 regulatory interactions in E. coli. Okay. So imagine this page, look at it. What if you only knew 1 out of 4 words? How much would you know? We don't really know much, do we? But this is real data and this is real life. When we deal with data, we're always dealing with imperfect data. For example, when you deal with medical records at a hospital, we have incomplete and missing data. When we're training self-driving cars, we have a finite number of of cameras. We have finite number of collecting data. And we have finite number of scenarios that we would like to examine and make sure that we use these finite amounts of data to train in a global scheme here. So yes, real data is messy and there's a lot of pieces missing, and sometimes even the data is contradictory. And in biology, this is more pronounced than any other area that I've worked in before. So let me remind you of some biology basics. I don't know if biology is required in college, but this is just a refresher, maybe from high school. Let me start out with describing the central dogma in biology. Basically, DNA gets transcribed into mRNA and it's translated using the ribosome into some proteins. Okay, this is how biology always works. The proteins, some of the proteins happen to be enzymes. And people like to represent enzymes as Pac-Man. I like to represent them as Miss Pac-Man. And I'll tell you why the Pac-Man analogy works just in a minute. So these enzymes, what they do is they control how reactions happen within cellular processes, right? Like in cells, like in your tissue, in bacteria, and so on. So the idea here is that the enzymes control these reactions. So if I have a reaction here that A and B turn into C, this enzyme actually regulates or catalyzes or speeds up this reaction. So in this network here, I have molecules A and B turning to C, molecule C turning to D, molecule D turning to E. D is also turning to F, and F is turning back to C. So these these reactions, right, they form a network graph where I have nodes are the molecules and the reactions are the edges of this graph. So I'm not interested in this regulatory process here. I'm more interested in this level of biochemistry and what's called metabolic networks. So let me tell you a little bit about enzymes and what enzymes do, and back to the Miss Pac-Man analogy. As I said, enzymes simply speed biochemical reactions. Remember your chemistry? You didn't have to have an enzyme to make a reaction happen, right? In biochemistry, you need this enzyme to make reactions happen. In this example, the enzyme interacts with the molecule. And in this case, we say the enzyme actually binds, the molecule binds to the enzyme. And the enzyme causes some change in the molecule. So for example, here, the enzyme is actually cutting this contact right here, this bond right here, and it's releasing a molecule, an hydrogen and an oxygen atom. I want to emphasize that this is a cartoon, okay? The enzyme is a protein, and proteins are usually much, much bigger than molecules, and I'll show that example a little bit later. So this part of my talk is about research going on in my lab. What I would like to do, I'd like to predict if an enzyme interacts with a molecule. For many, many years, there was a prevailing belief that enzymes are specific. Each enzyme has one particular structure. Here's a protein or enzyme that's folded in a particular way, and it has the ability to interact with only one specific molecule. And that's part of our discovery process, right? The people that worked in biochemistry early on didn't know much, and this is what they had thought initially. But as it turns out, enzymes, like the one I've shown here, interact with other molecules other than these, the ones they evolved to interact on. So if you look at these molecules here, and you have to look at these molecules very carefully, unfortunately, I didn't draw them in a very symmetrical way. It turns out that this molecule is very similar to these other two. So the enzyme, which is this protein that's folded in a particular way and has this pocket, that's the mouth of the Miss Pac-Man, is actually the shape of the pocket matches a portion of this molecule. And that's why different molecules bind with the enzymes. So here's the problem that I'm trying to solve. Even though we've cataloged lots and lots of biochemical reactions and interactions between molecules and enzymes, there's so many others that are uncharacterized. There's over 100 million known molecules in the universe that's cataloged in the universe, not existing in the universe. And there's millions of enzyme sequences that we already know about, but there's so many more that remain uncharacterized. So my goal is to use machine learning to characterize enzymes in terms of their ability to act on molecules. So I'll give you a few examples of some work that we're doing in this area. To make this enzyme work on this molecule, and for me to predict what is going to happen when this enzyme acts on this molecule, I have to know where the site of metabolism is. I need to know if this enzyme is going to act on this bond, or on this bond, or on this bond, or on this bond. And we typically think about the enzyme acting on a reaction center. So here, maybe I think this is the reaction center, or this one, or this one. And my goal is to predict the likelihood of a specific enzyme acting on any of these reaction centers. So to do that, we actually built something called graph neural networks. They're neural networks like I described earlier, in the sense we train them as neural networks, but they actually take advantage of the graph structure. Remember, the molecule is like a graph. You could think about it as having nodes. Each atom is a node, and each bond is an edge in the graph. So what we could do is we could design these graph neural networks to incorporate overall molecular structure and incorporate atom properties. Okay. So in our example here, to predict the size of metabolism, I end up saying there's high probability that this particular enzyme is going to act on this reaction center. And I have low probabilities on other parts of this molecule. So again, knowing how to predict the site of metabolisms helps me understand how enzymes act on particular molecules. The next question we're interested in is predicting enzymes that act on a particular query molecule. In this case, the enzyme is specified using what's called an enzyme commission number. Enzymes are categorized using these numbers. Class 1 of enzyme does a particular function, and class 1.4 does a more specialized function, and class 1.4.1 does a more specialized function. And class 1411 acts on a very specific molecule or a group of molecules, like I showed you earlier. The goal here is we want to predict the likelihood that a particular enzyme acts on a molecule Q. It turns out this problem is very similar to the classifier problem that I talked about of predicting cat or dog. Instead of cat or dogs, we have many class labels. So I have class label 1.1.1.1 and 1.11.2 and so on. So this is not just a binary classification problem. This is actually a multi-class label classification problem. So in this case, the input is not an image, it's a molecule. Okay, and the output is going to be just what's the likelihood, what's the probability of this enzyme acting on the input molecule? What's the output of this one, this enzyme acting on this molecule? Now, one of the things that we have to talk about and figure out is how do we feed a molecule into this neural network? So what we do is we use things called fingerprints, molecular fingerprints. A fingerprint is just a binary vector where it indicates the presence or absence of particular groups or functional groups. So for example, this one can tell me the molecule has a ring. This one could tell me that the molecule has a CH3 group. This one could say, I have a triple rings. So, and that's not present in this case. So again, the goal here is to train this multi-label classifier to predict if an enzyme is going to act on these molecules. So we need data, we need lots of data. And it turns out we could use existing data obtained from databases that catalog enzymatic reactions. And we're able to predict these enzymes acting on molecules with a high accuracy. And if you were interested, I have a paper here on the archive that you can look at. The next question we wanted to answer is how do we recommend particular molecules or enzymes? Or how do we recommend particular enzymes to molecule? This idea is very much rooted in recommender systems typically used in Netflix or Amazon. Netflix uses a recommender system to recommend movies to users. It also uses the recommender system to connect users to movies. So the recommender system tracks user properties. For example, Jamila loves movies from the 70s with Hussein Fahmy, or Camila loves James Bond movies from the 90s. The recommender system also keeps tracks of properties of the movies. For example, it's a rom-com, or it's a drama, or a comedy, or a sci-fi movie. So we wanted to do something similar for our enzymes and molecule to help synthetic biologists that are looking for specific enzymes that act on a particular molecule they're interested in. So we use the properties of the enzymes and properties of the molecules, and we build these recommender systems to make these recommendations. The next question we wanted to know is what's the likelihood of a biochemical reaction existing between two molecules? And before I tell you what I did, I want to tell you about this just amazingly powerful concept in machine learning. It is possible to create representations of nodes within a graph, use something called graph embedding. The idea is very, very simple. Here I have a graph, and clearly the green nodes 1, 2, and 3 are more connected to each other than, say, nodes 1, 8, and 1, 9. So what I could do is I could learn, for example, a 2D representation, an X and a Y coordinate for each node in this two-dimensional space. So it turns out the coordinates for nodes 1, 2, and 3 are closer together than, say, 1 and 9 and 2 and 9. Okay. And of course, I'm not just going to build this representation in a two-dimensional space. I'm going to build it in a multi-dimensional space. And now what I have is I have embeddings or representations of the nodes in this multi-dimensional space. And I could ask something like, what is the distance in Euclidean space between two nodes? Okay, for example, 1 and 9 are much further apart than 1 and 2. So let's say I wanted to predict, does 1 interact with 9? Well, 1 and 9 are very far together. I could ask, does 1 and 4 interact? Well, 1 and 4 are much closer together than 1 and 9. And this is the same idea in social networks, right? If you're 2 hops away from person number 4, if you're number 1, and you are 1, 2, 3, 4, 5 hops away from person number 9. So again, we were able to train these deep neural networks to learn these representations and predict with high accuracy if there are links in our network. The other thing that we did that was super exciting is looking at how to use natural language processing to study this enzyme. The enzyme, this is an enzyme, as I told you, the Miss Pac-Man, and here's the molecule. If I take this enzyme and super stretch it out, okay, it looks like a sentence. The sentence has words in it. The words just happen to be very limited vocabulary. I only have 20 types of words in my sentence. So it turns out that we can use natural language processing techniques, including BERT, which is state-of-the-art in machine and natural language processing. It's used in Google Translate to learn these molecular interactions. So thank you for listening to the details of my work and on using machine learning to advance biology and biotechnology. I hope the examples that I showed you about AI being transformative and the specific examples from my research have shown you that we're just at the beginning of a journey to discover more about AI and how to use it to make a better planet and to make life better for all humans. I would like to leave you with a few thoughts. I'd like to mention that we need to think about new ways of using AI. We can't just take a system out and replace it with another system. And I'd like to tell you a very short story about this. Before 1880s, factories used steam engines to run to provide energy to the factories. The steam engines were placed at the center of the factory to make it easy to distribute energy around the factory. Electrical systems came in the 1880s. So what they did is they took out the steam engines and they put the electrical system also in the middle of the factory. It took them 30 to 40 years to finally realize that, hey, the electric system doesn't need to be in the middle of the factory. And if you notice now, nobody puts their electric systems in the middle of factories or rooms. So I want to point out that we should not be limited by what currently exists, but we should be limited by our imaginations. Some advice: be trilingual. Okay, learn your math and stats, do your hacking, really learn something about the problem that you're trying to solve. Engage others, don't do stuff on your own. Even when you have people that say no to you, figure out why they're saying no. They're probably telling you something that's really important and you need to incorporate it in what you do. And you want to get them on board to buy into your ideas. I want to remind everybody to be mindful of fairness. There's a lot of bias in data. The face recognition system that I showed you turned out to be very biased against Black people. And that's because the training data was biased. Sometimes the algorithms themselves are biased. So we really need to be thoughtful about that. And we need to think about inclusiveness. Who does the software that we build serve? And we need to think about privacy, and we need to think about securities. We need to think about, should we collect this data? Should we share it? And how do we really anonymize the data? Data security says we need to figure out how to protect our data from unwanted actions of unauthorized users, such as cyber attacks or data breaches. There are many, many women that left their mark on modern day technologies. Here are a few of my favorites. I just want to highlight a couple of them. Hedy Lamarr is an actress and an inventor who pioneered the technology that would be one day form the basis of today's Wi-Fi, GPS, and Bluetooth communication. She actually filed a bunch of patents, but they did not she didn't benefit from them in time. So she was too early, if you will. Annie Easley was a computer scientist, a mathematician, and a rocket scientist. She was leading a member of the team that developed software for the Centaur rocket stage and was one of the first African Americans to work on as a computer scientist at NASA. There's many, many other wonderful people, including my friend, Roger Coleman. Okay, so just to wrap up, I would like to very much thank members of my group. I have an amazing group of students. Some of them are undergrads, just like some of the people in the audience. Some of them are graduate students. I have some truly amazing collaborators. You know, that bit about engaging others. I actually work very hard to engage people in my research. I don't do research on my own. I have collaborators that are biotechnologists, Nick and Kyung and Jim. And I also have some amazing machine learning collaborators that I learned a tremendous amount from, including Mike and Levin. And I'm thankful and grateful to funding from the National Institute of Health and the National Science Foundation. So, technology in engineering and science is a journey. The path is not necessarily a straight one. We're constantly discovering new things and reinventing ourselves and everything around us. May the invention powers of AI be with you. I'm always looking for great grad students. So if you're an undergrad, you're finishing up your undergraduate degree in computer science or related area, please email me. As I said, I'm always looking for great students, and I would like to just take some questions from the audience. Thank you.
Thank you very much, Professor Suha, for the enlightening talk. As a bioinformatician myself, I truly appreciate the effort of your research team on trying to decode biology in its essence and trying to help the humanity understand more about this mystery, the big mystery of biology. We have time to take a couple of questions. So for the audience, please, if you have any questions, raise your hands. And while the audience raise their hands and prepare their questions, I have a question myself. So you mentioned on a very important and critical aspect when it comes to finding solutions for biology computationally, which is the biases that could occur or could be inherited from the existing systems or the algorithms, etc. So as a bioinformatician myself, I know about this study bias that we suffer as computer scientists, that when we try to build intelligent systems and machine learning approaches, that is present in the experiments that are done by biologists. For example, in molecular networks, there are such study biases when certain proteins or genes tend to be heavily studied compared to others. So which kind of limits really the potential for the whatever models that we are trying to build. So what are your thoughts on this matter, and what are the current trends in dealing with such study bias?
That's a super amazing and excellent question. So in biology, the trends are you don't pick just one data set to evaluate what you're doing, okay? So you could think about, and we actually had to do this for many of our studies, you could think about just randomly splitting your training and evaluation data or validation data, right? You could also think about biasing the split. For example, you could have the training data have items that are more similar to each other, and then you're trying to see what the, how does your system do on data that it hasn't seen before, okay? So that's a different way of evaluating it. You could also look at the sensitivity of your machine learning algorithms for changing features, right? So if I change the color of the skin, what would be the bias in my face recognition, right? That should be non-trivial. So I think we're arriving at a point where we start evaluating models, machine learning models, in much more thorough and careful ways.
Thank you very much for your remarks, Professor Suha. We have a question from one of the audience, Dr. Mona Shahrani. You can unmute yourself. Okay.
Hi. Hello.
Hello, Mona.
Yes, can you hear me?
Yes.
Yes, we do.
Thank you very much for this nice and smooth talk. I have actually two questions about your work because I work in a similar area of learning graph representation. So I would like to ask you a question. So you're using graph representation learning to predict enzyme interactions. So which method or technique would you find most successful based on your work on this in this field or in this area?
Thank you for asking that question, Mana. So we have done is we have looked at pretty much every graph convolutional graph attention type model that there is. What we're finding is that neural networks are more of an art than a science at this point, in the following sense. I really can't predict which model is going to work better than another, right? I just don't know. So what I typically do is set up my data sets that I want to do the evaluation on, and I run through lots and lots and lots of models. And then I figure out, so what I do is I build my data into training, into validation, and test. I use my validation data to actually select the best model among all of them. And then I evaluate and report the results based on my test data set. I think that's where we are in machine learning, and I don't think there's any single thing that I could tell you ahead of time works well.
Yes, that's why I'm asking this question, because some graph learning algorithms are better at predicting specific features, others are better at specific features. But I mean, in general, and in using it for chemical interactions, I just was curious if there is one that could be a winner in this field or something like that.
So for for every study, we just evaluated like 10 different models.
Yes, I understand. Okay. Also, how big your graphs are? For example, you're using PubChem graph database, or so. How big is the graph? I mean, do you select subsets of those graphs to predict the interaction, or do you apply it on the whole graph of, for example, PubChem?
Thank you. That's also very good question. So we're interested in specifically in biochemical interactions. So we usually go to databases that record biochemical interactions. So there's a database called KEG. There's another base called PubChem. That's called Brenda. And those have biochemical interactions. And then what we do is we go to PubChem to get sort of properties of the molecules or any kind of additional information that we need to do the task.
Okay, great.
So I don't know what area we work on exactly, but if you want to send me any email questions, I'm happy to answer them as well.
Yeah, thank you very much. That was a nice, very inspiring talk. Thank you.
Thank you very much, Mona, and big thank you to Professor Suha for this amazing and